Imagine a ghost particle, a particle that physicists have been searching for almost a century, but which seems to evade every attempt at capture. We are not talking about science fiction, but about the most mysterious and elusive particle in modern physics. The graviton. This hypothetical particle is supposed to mediate the force of gravity, just as the photon mediates light. But there is a problem. No one has ever seen it, and worse still, the mathematics that should describe it seems to go haywire, producing untamable infinities. Today, we will explore together one of the greatest enigmas of contemporary physics, a mystery that challenges the very foundations of our understanding of the universe. If you are passionate about this type of content, I warmly invite you to subscribe to the channel and activate the bell so you don't miss the next videos. And now, let's dive into the mystery of the graviton. To understand why the graviton is so special, we must start with the standard model of particle physics. This is probably the most sophisticated and experimentally verified scientific theory that humanity has ever developed. The standard model describes all the fundamental particles and 3 of the 4 fundamental forces of nature. On one hand, we have fermions, the particles with half-integer spin that make up matter. Among these, we find the quarks, up, down, charm, strange, top and bottom, which form protons and neutrons. Then there are the leptons, such as the electron, the muon, the tau particle, and the neutrinos. These particles are named after Enrico Fermi, the great Italian physicist. On the other hand, we have bosons, the force-mediating particles. The photon mediates the electromagnetic force. The gluon holds quarks together through the strong nuclear force. The W and Z bosons mediate the weak nuclear force. And then there is the Higgs boson discovered in 2012 at CERN, which gives mass to other particles. But in this extraordinarily complete and verified picture, something fundamental is missing: gravity. There is no particle that mediates the gravitational force. This gap in the standard model is not a negligible detail. It is one of the most profound questions in modern physics. The Lagrangian of the standard model, that complex mathematical expression you often see on physicists' t-shirts, contains terms for all known forces and particles. There are the field tensors for the forces, the terms describing matter, and the Higgs sector that breaks symmetry. But gravity is simply not there. So, what should this graviton be like, assuming it exists? Theoretical physicists, working with equations, have deduced some characteristics that this particle should have, characteristics that make it profoundly different from all other known particles. First of all, the graviton should have a spin of 2. This is a remarkable result, and to understand it, we need to do a little thought experiment. Imagine a box full of electrons. If you observe this box from different relativistic moving frames of reference, what physicists call performing a boost, you can study how the charge density and current of the electrons transform. What you discover is that the source of the electromagnetic field is a 4-vector, a mathematical object with 4 components. This naturally couples to a mediating particle with a spin of 1, the photon. But if you do the same exercise with energy density, which is the source of the gravitational field, you discover something different. The source is a rank 2 tensor, a more complex mathematical object. This requires a mediating particle with a spin of 2. The graviton would be the only elementary particle with a spin of 2. And here it gets even stranger. It should have 0 mass because gravity has an infinite range. It should be electrically neutral. And crucially, it cannot be a particle composed of other particles. This last point is guaranteed by a theorem in theoretical physics called the Weinberg-Witten theorem. This theorem establishes precise limitations on what types of particles can exist. It tells us that massless particles with a spin greater than 1/2 cannot carry Lorentz covariant currents, and massless particles with a spin greater than 1 cannot carry a Lorentz covariant stress-energy tensor. In simpler terms, the graviton, if it exists, must be a fundamental elementary particle with a spin of 2. There is another crucial difference compared to the photon. While photons do not interact directly with each other, gravitons do. Gravitons gravitate, they attract each other. This makes the theory immensely more complicated because one must consider interactions among the force-mediating particles themselves. And here we arrive at the heart of the problem, the reason why the graviton is so elusive. Quantum gravity is not renormalizable. But what exactly does renormalization mean? Renormalization is a sophisticated mathematical technique used to make physical theories predictive by eliminating or absorbing the infinities that appear in calculations. Let's use a concrete example to understand. Imagine you want to measure the speed of your car. You start with a theoretical value, a prediction based on your model, but then you have to make corrections considering air friction, engine power, and wind. When you perform these more precise calculations, terms that tend towards infinity can appear. The solution is to redefine the velocity by directly using the one measured experimentally, so that the infinity is absorbed into the measurement itself. It's not that the infinity magically disappears, but it is hidden in a way that makes the theory usable and predictive. This, in a nutshell, is renormalization. Many physical theories are renormalizable. Quantum electrodynamics, the theory that describes photons and electrons, is renormalizable and is in fact the most precisely experimentally verified physical theory ever. The theory of weak and strong interactions is also renormalizable, but gravity is not. When physicists tried to treat gravity as an ordinary quantum field theory, infinities emerged that could not be absorbed. The problem is that as the theory is refined and more complex processes are considered, what physicists call loop corrections, more and more infinite parameters appear. It's as if mushrooms were sprouting. Every time you remove one, others pop up. There is not a finite number of these parameters that can be regularized. It is important to emphasize that this is a well-established mathematical result in the scientific community, not speculation. The equations simply produce these uncontrollable infinities when one tries to quantize general relativity using the standard methods of quantum field theory. Faced with this seemingly insurmountable obstacle, theoretical physicists have developed alternative approaches to try to unify gravity with quantum mechanics. The two main paths are string theory and loop quantum gravity. String theory proposes that, at the most fundamental level, particles are not points, but tiny, vibrating strings. These strings would exist in a space with more than 4 dimensions. Some versions require up to 26 dimensions, where the extra dimensions are compactified into complex mathematical structures called Calabi-Yau manifolds. In this framework, the graviton would naturally emerge as one of the vibrational modes of the string. Loop quantum gravity, on the other hand, proposes that space-time itself is discrete at the most fundamental level, consisting of an intricate network of space-time atoms connected in structures called spin networks. In this approach, the smooth space-time we perceive would be an emergent approximation, valid only at larger scales. It is essential to be clear. At present, neither of these theories has been experimentally verified. They are sophisticated and internally consistent mathematical frameworks, but they still lack testable predictions or direct observational confirmations. The scientific community continues to work on both approaches, along with other lesser-known ones, in the hope of finding a final theory that unifies gravity and quantum mechanics. But let's pause for a moment. Beyond the mathematics and equations, what does all this tell us about the profound nature of reality? The question of the graviton touches on some of the most fundamental questions humanity has ever asked itself. First of all, it forces us to confront the limits of our knowledge. We have a theory of gravity, general relativity, which works magnificently at large scales. We have quantum mechanics, which perfectly describes the microscopic world. But these two theories seem fundamentally incompatible. This suggests something profound. Perhaps reality at its most fundamental level is radically different from how we perceive it. The space and time we experience might not be fundamental features of the universe, but rather emergent properties deriving from something more basic that we cannot yet adequately conceive. Think about what it would mean if spacetime were truly discrete, made of tiny quantum pixels, as loop quantum gravity suggests. This would challenge the very idea of continuity that we have inherited from Greek geometry. Or if strings were real, we would be living in a universe with hidden dimensions, invisible to our direct perception, but nevertheless fundamental to the very existence of matter and forces. There is also an important epistemological question. We are probing energy regimes and distance scales, the Planck energy and the Planck length, that might forever be inaccessible to direct experimental verification. This raises profound questions about what it means to do science when we cannot directly test our theories. And then there is the question of mathematics. Why does nature seem to follow such precise mathematical laws? And why, when we try to extend these laws to their logical limits, does mathematics itself seem to break, producing infinities and inconsistencies? This could be a sign that we are using the wrong conceptual tools, or that there is something fundamentally different in the way nature operates at its deepest level. Some speculations, and it is important to emphasize here that these are philosophical speculations, not scientific claims, suggest that the search for the graviton might also have implications for our understanding of consciousness. If gravity is fundamentally different from the other forces, if it operates at the level of the very structure of space-time, could it play a special role in the emergence of complex properties like consciousness? Physicists like Roger Penrose have explored this possibility, although it remains highly controversial and unverified. Despite all these theoretical difficulties, physicists have not given up. The search for the graviton, or more precisely, for a consistent quantum theory of gravity, continues with growing intensity. There are also indirect experimental attempts. Some researchers hope to observe quantum effects of gravity in experiments with increasingly sensitive interferometers. Others search for traces in cosmological observations of the early universe, in the cosmic microwave background, or in gravitational waves. Gravitational waves themselves, first detected in 2015 by LIGO, are a fascinating phenomenon. They are predicted by classical general relativity and brilliantly confirm Einstein's predictions. But they tell us nothing directly about gravitons. The gravitational waves we observe are classical phenomena involving billions and billions of hypothetical gravitons behaving collectively. It's like the difference between observing the light from a light bulb and detecting single photons. Both exist, but they require very different instruments and approaches. A direct observation of a single graviton would require detectors of impossible size. We're talking about detectors as large as Jupiter And this brings us back to the epistemological questions we were discussing earlier. Are there fundamental limits to what we can directly observe? We have reached the end of this journey into the mystery of the graviton, and perhaps you have more questions now than when we started. But this is precisely the sign of great science, not that which provides definitive answers, but that which pushes us to ask deeper questions. The graviton represents more than just a missing particle in a table. It is the symbol of our incompleteness, of the unresolved tension between the two great theories of the 20th century, general relativity and quantum mechanics. It is an invitation to humility, a reminder that despite the extraordinary progress in physics, there are still fundamental mysteries about the nature of reality. But it is also an invitation to optimism. Every great obstacle in the history of physics, when finally overcome, has led to unexpected and revolutionary discoveries. Understanding quantum gravity could reveal a universe even stranger and more wonderful than we can imagine. Perhaps space and time are not continuous, but discrete. Perhaps there are hidden extra dimensions. Perhaps reality at the fundamental level is made of vibrating strings or spin networks. Or perhaps the truth is something completely different, requiring concepts we have not yet invented. What is certain is that gravity is speaking to us. Through the gravitational waves propagating in the fabric of space-time, through the dance of galaxies and the expansion of the universe, it is whispering secrets about its own nature. Its quantum alphabet has yet to be deciphered, but every equation we write, every experiment we conduct, brings us one step closer to understanding. And perhaps, one day, we will look back on this era and smile, remembering when we were desperately searching for the graviton, that ghost particle that turned out to be, well, we will only find that out by continuing to search, to calculate, to imagine. If you enjoyed this video and want to continue exploring the great mysteries of physics together, I invite you to subscribe to the channel and activate notifications. Serious and accurate science communication requires time and effort, and your support is fundamental. Thank you for watching, and remember, the universe is much stranger than we can suppose. Keep asking questions, keep searching, keep wondering. See you in the next video.